So the last part of of this week's lecture, right? This is week 10. So we will now look at another type of phase diagram where basically, so we have looked at a phase diagram where we have zero solubility in the solid state, but infinite solubility in the liquid state, right? And we have looked at this, and we have basically assumed the liquid to be an ideal solution, and we have found out how it looks like, and we have defined an intake point, and we told that there is zero solubility in the solid state. If you remember, we told zero solubility means basically Xa equal to 1 in the solid state, or Xb equal to 1 in the solid state. So in the solid state there is no, right, when the solid phase, so solid is basically pure A and pure B, right? So basically A and B do not mix, A plus B do not mix because are not soluble in one another, right? So A plus B are not formed, do not form a solution, do not form. So in this case, A plus B do not form solution, and where when Xa, so basically if I look at that, we told this basically XAS equal to 1, XBS, that is in the solid state, this is equal to 1, so A and B, so this is for the solid state, right? This is the solid state. But in liquid you have infinite solubility, right? In liquid is a complete mixture of A and B. Now you have, in the second case, basically an AB alloy. So in the second case we are talking about an AB alloy, again a binary alloy with infinite solubilities in both liquid and solid, and you have isomorphous components. As I told you, isomorphous means having the same structure. And you get some sort of a lens diagram, and this lens diagram basically is very common. For example, and you can see them in copper nickel. For example, copper nickel is one very important example in this type of diagram, where copper and nickel have the same FCC structure, and they form an entire over the entire composition range, they form a solid solution or a liquid solution, right? Over the entire composition range, copper and nickel will form a liquid solution, or over the entire composition range, the copper and nickel will form a solid solution, and they are isomorphous. That means copper is FCC, nickel is FCC, and they form, and the structure remains the same, right? They have the same isomorphous means the same structure, and the same structure is there from 0, xb equal to 0 to xb equal to 1, and you basically get this type of a lens shape diagram. So this lens has one part which separates liquid from the two-phase liquid plus solid, and there is the other part which basically separates liquid plus solid from solid. So this part basically has one name, and this part has another name. So basically the part that separates here, so this curve, this guy basically is called liquidus. So it is basically separating the two-phase region from the liquid plus solid, and this part is called solidus. And again, as you know, within the so in the single phase solid or in the single phase liquid, you cannot draw a tie line, and you have degree of freedom, which is basically 2, right? It is basically 2. But within the liquid plus solid region, you can basically draw a tie line. So at a given temperature, say for example, I have a given temperature, say, look at this. Say I have a temperature here. So basically, remember, you cannot draw tie line in the single phase region. Now, if you look at this guy, see, this is happening at some temperature. So I'll just mark the temperature. So let this be T1, and in this T1 temperature, basically, we have this tie line. Right, this tie line is there. This is a temperature T1, and now at this tie line, so from this tie line that we draw in the two-phase region, you can now basically drop these vertical lines, right, which are parallel to the. So basically, you have this one line here, one line here, and you can have another line you can draw here, and these basically tells you, this line and this line basically tell you that this is the, so at temperature T1, right, at temperature T1, at temperature T1, you basically have, this is the composition, so this is XB, this is the liquid composition which is in equilibrium, so XB liquid in equilibrium with solid, so liquid solid, and this is basically XB solid which is in equilibrium, and this is a solid, right, so this is solid liquid equilibrium, right. So you have these two compositions, right, this composition and this composition at temperature T, where the chemical potential, so at this temperature the chemical potential of this of the liquid phase and the chemical potential of component B in the liquid phase is equal to the chemical potential of component B in the solid phase. So basically, if I want to look at what are these, we are basically going to solve two equations. One is called mu A liquid equals to mu A solid at temperature T1, at T1. Remember, this is at temperature T1. And then we are also going to solve another equation, which is mu B liquid equal to mu B solid. Now, if you have that, then you basically get these two compositions. So if you solve this, you basically get these two. So if you solve, once you solve this, you get this composition and this composition. So this is the composition of the liquid which is in equilibrium with it. So this is the composition. So at temperature T1, this is the composition of the liquid phase. This is the composition of the liquid phase, right? This guy. So we read the compositions from the x-axis. So this is the composition of the liquid phase, and this is the composition of the solid phase. And these two compositions are basically solution of these two conditions, or that means, and this composition is in equilibrium with this composition. So this composition of the liquid phase is in equilibrium with this composition of the solid phase, right? So that's the idea. Right, but it's a lens shape diagram. Now if you look at this, you have now in both cases complete solubility, right, infinite solubility. Now again you look at the same thing, ln xas by xal. So you are now looking at ln xas by xal, which you have delta HA0 melt, that is the pure melting transformation latent heat. This is the latent of melting of pure A. This is the latent of melting of pure B, your R, which is gas constant, your TA freeze minus TA0 freeze, and TB freeze minus TB0 freeze, right? Now, if you have that, so basically TB freeze or TA freeze, like the freezing point of component A or freezing point of component B, but since it is infinitely soluble in both, so basically TA freeze and TB freeze are basically going to be the same across all, right? They will vary, right? They will be the same width, they will have the same T freeze. So if you, instead of writing TA freeze or TB freeze, we can directly write T freeze, and the T freeze is basically for an alloy which is not pure A, neither pure A nor pure B. Now in such case, you see another thing, that XAS plus XBS equal to 1, XAL plus XBL equal to 1. So basically what I am trying to say is that if I look at vertical line, if I am looking at a vertical line, say for example, I can get a very thin line here, draw a very thin line here, thin vertical line here, and we can look at the freezing point. So basically, if you look at this is this point is TA0 freeze, and this point is TB0 freeze, and as you can see, TB0 freeze is greater than TA0 freeze. That is the melting point of B, or freezing point of B is greater than that of A, right? That is what we are basically looking at. Now, if you look at this line, you have one point where liquid starts changing to solid, right? Liquid starts. So basically, it is not that liquid is transferring to solid, but it is transferring to solid because some amount of solid is starting to liquid, right? Some amount of solid is starting to liquid. Now, remember that when this liquid to solid transformation took place here, for example, liquid plus A, now this remaining liquid now will completely go to B, and so that is where you saw this horizontal segments, right, in the cooling curve. Now here how will it happen? We have to see, right? We will require to see. So we'll one thing, XAS plus XBS will be equal to 1 and XAL plus XBL equal to 1. So as a result, we are now looking at only XB, the variation in XB. So this is pure A, right? This is pure A, and this is pure, right? And now you have XAS, that is the XA in the, so basically S again is the solid, right? S is solid. So you can put a bracket here if you want, but I generally prefer this. So you have XAS and you have XBS. So this is the solid phase. This is basically, so S denotes solid phase. There is only one solid phase because you have an infinite solubility in the solid solution. So one S is a solid phase and one L is a liquid phase. But if you see the previous diagram, you had pure A solid and you have pure B solid, right? But here you have S, which is a solid phase. It's a mixture of copper and nickel solid. So it's or A and B solid solution, right? Isomorphous mixture of A and B. Or isomorphous mixture if you think of copper and nickel system. So it's a copper nickel system, then isomorphous solid solution of copper and nickel. So here it is isomorphous solid solution of, so this S is isomorphous solid solution of A and B, right? So you have that and you have L. So similarly you have for liquid XL plus XBL equal to 1. So basically liquid is, L is stands for liquid phase. And there is infinite solubility in both. Now, if I want to, so you have equation number 1 here, equation number 2 here, and you have equation 3 here, and you have equation 4 here. Now, if you solve them, you basically get XBS and XBL, right? You get XBS is the equilibrium composition of not equilibrium, the solid composition, so the solid composition, right? The mole fraction of B in the solid, mole fraction of B in the solid as a function of temperature, right? You take mole fraction of B in the solid as a function of temperature, or mole fraction of B in the liquid as a function of temperature. Now this guy, this XBLT is what basically, so this one is going to give me the liquid S, right? This is the liquid S equation. So you can see this is the liquid S equation and XBST is the solid S equation, right? Because at different temperatures, right, it is basically having as a function of temperature, right? It goes from one temperature, that is pure melting point of pure A, to melting point of pure B. It is basically, if you look at the solid as the way it changes, it's like this, or liquid as it changes, right? So that's the idea. Now we can also replace, basically if you want, we can basically, if this is where we are basically assuming ideal solution. So I am telling ideal solid solution, and we are also looking at ideal liquid solution. But we can also do the non-ideal ones. So basically if we look at non-ideal, then XAS is replaced by activity of A in the solid, and XAL, that is the mole fraction of A in liquid, is replaced by activity of A in liquid. Similarly, XBS is replaced by ABS, and XBL is replaced by ABL. Now you have this relation that you can write, right? Del N AS del XS. So basically this comes from the gives to N, right? So if you write this equation as a function of pressure, so keeping pressure and temperature fixed, right? You have to make sure that pressure and temperature are fixed. you can basically write del ln AS by del XAS, and this is del ln ABS by del ln XBS, and you have XAS and XBS, which basically comes. Similarly, you can, this is for the solid, right? This is for the solid, and you can also write this for the liquid. So you have now for liquid you have XL, del ln. So this is del ln A, del ln X, and this is del ln A del ln X for B, right? So this is for B and this is for A, and if you have this two equations, so this is basically coming from the Gibbs-Duhem relation, okay, and you also have the XA. So basically remember AAS, so this is something that you have to remember. Although XAS plus XBS equal to 1, AAS plus ABS for a non-ideal solution, right, it is not equal to 1 because this has a gamma, right? And so basically AAF is gamma AS in the solution in X. As a result, this is not equal to, the activities do not sum up to 1. So basically you have two equations, so basically you cannot directly solve it, right? It's not so easy to solve, right? That is one thing that you have to remember. When you have a non-ideal solution, you have these two equations, and you can write XAS plus XBS is equal to 1 and XL plus XB equal to 1, and you will get, now you have how many variables? You have these variable, right? And this is also a variable, this is also a variable, and this is also a variable, right? So you have 4 variables, but you do not have any other equation, right? You have only this equation and this equation, right? So as a result, it is not straightforward, it is not very straightforward to get the liquidus and solidus curves. But however, there are ways to basically obtain these curves. There are ways to obtain these curves, but it is not as trivial as here. So here you have like clearly 4 equations, and you have basically within these 4 equations you can basically get XBS as a function of temperature and XBL as a function of temperature. Again, you will also tell me that if I do this XBS as a function of temperature or XBL as a function of temperature, I have basically two variables, right? Why do I require these 3 and 4? So 3 and 4 gives a restriction, and which you can use to basically get into this XBS and XBL, right? So, and as a result, you can get XAS and XAL. So here also, basically, you are looking at 2 equations, but remember, you have to measure the activities, right? You have to measure the activities. You have to know how the activity will vary, right? For this non-ideal case, you can always assume some regular solution model, right? You can assume. So in this case, non-ideal solution, you can approximate. So you can approximate using a regular solution model. This is one approximation, regular solution approximation. Now if you do that, so you can use regular solution approximation. That is one type of an approximation. There are many other non-ideal solution models, but regular solution is a well-known positive model, and you can use it. Now if you look at the lens again, as I told you, you have this tie line. So you have this tie line, this guy at temperature TQ, right? At temperature TQ, you have this tie line, and you have P and R and Q. Q is your alloy composition. Now if you see line PR is the line that is drawn. This is a tie line at TQ. So basically I can draw a tie line which is slightly thicker. I can draw a tie line here, right? So this is the tie line that you only draw in the two-phase region. Now in this two-phase region, this tie line intersects the liquidus curve at T and intersects the solidus curve at R, and basically you can see if XBQ, see this XBQ is the alloy composition, then amount of phases liquid, so basically Q, so basically the amount of liquid phase, right? Amount of liquid phase is given by QR by PR, right? QR by PR. And amount of solid phase or fraction of solid phase is given by PQ, right? Now how does it come? So we can look at the lever rule. okay, and derived. So this is basically, if you look at this, phi L plus phi S equal to 1. You can see that because QR plus PQ is nothing but PR, and PR by PR equal to 1. Right? Now I'll just end this with the derivation of lever rule. I'll just end this with the derivation of lever rule, and you have like NT, which is the total number of moles of components A and B, and Na is the number of moles of A, Nb is the number of moles of B, and Nl is the number of moles of liquid phase, and Ns is the number of moles of solid phase. So Na is the number of moles of A. So Na, basically, if I look at that, you can write it as Na in liquid plus Na in solid, right? And here also liquid plus Nb solid, right? So basically these are distributed, but NL, basically if I tell NaL plus NBL equal to N. Similarly, NAS plus NBS. So there is the amount of, or the number of moles of solid phase, right, or number of moles of liquid phase, right. But these are like Na is the number of moles of A that is distributed between the liquid phase and the solid phase. Nb is the number of moles of B that is distributed between the liquid phase and the solid phase. The overall alloy composition, as I told you, is XBQ, right. Now, if you look at that, so basically it's a composition of two-phase mixture. Now, if you see XBQ as the mole fraction of B, and that is the overall alloy composition, right, at temperature TQ, then the number of moles of B is basically equal to total number of moles, right, total number of moles times XBQ, right, so NB, number of moles of B, or NB, is equals to nothing but NT is the total times XBQ, right, times XBQ times NT gives me NB, right. So you have moles of B in alloy, which is NT XBQ, and moles of B in liquid phase, which is NL XBQ. So moles of B in the liquid phase, which is basically given. So if you look at moles of B in the liquid phase, so if you look at moles of, so this is XBP, right, in the liquid phase the composition is XBP at this temperature, and XBR is basically the moles of, so mole fraction of the mole fraction of the, so basically this is the composition, right, this is the solid composition in equilibrium with the liquid composition. So XBR is the solid phase composition, right, XBR is the equilibrium solid phase composition at temperature TQ. This is the solid phase composition. So basically if I look at that, you have NL XBP and NS XBR is the moles of B in solid phase, right. So moles of solid, so NS is the number of moles in the solid phase. Now you multiply it with XBR, then you basically get moles of B in the solid phase. And for liquid phase, again you are looking at the equilibrium composition in the liquid at temperature TQ, which is basically given by XBP. XBP times NL, where NL is the number of moles of, NL is the number of moles of the liquid phase. Now if you see moles of B, so there is a conservation of component B. As a result, moles of B in liquid plus solid mixture equals to moles of B in L plus moles of B in S. So if you see that NT XBQ equals to NL XBP plus NS XBR, right? So basically NL XBP and NS XBR, where NS is the number of moles of solid and NL is the number of moles of liquid, multiplied with the equilibrium composition of this. In XBP is the equilibrium composition of the liquid, and this is the equilibrium composition of the solid at temperature TQ. So if you do that, this basically gives me number of moles of B in the solid phase, right? Number of moles of B in the solid phase, and this number of moles of B in the liquid phase, and together that is basically the total number of B in the solution, right? Now if you divide both sides by NT, what you get is XBQ is NL by NT into XBP plus NS by NT into XBR. Now phase fraction phi L is NL by NT and phase fraction phi S is NS by NT. So basically now if you look at that, XBQ is phi L XBP plus phi S XBR. Now phi L plus phi S, as you can see from here, phi L plus phi S equal to 1. So you can now write XBQ, and you have XBP, you have XBR, right? And you can write this as phi L XBP plus 1 minus phi L XBR. So basically this becomes, now if I do that, so you have XBR into 1 and X minus, so basically you have minus phi L and here it is plus phi L. You can take phi L common. This is XBP minus XBR. Alright, XBP minus XBR. If you look at that, this is basically XBP minus XBR or XBR minus XBP. Only thing, XBP minus XBR will be negative. XBR minus XBP is positive. Now, if you look at that, so you get phi L. So you have this equation. So this equation is there. This equation is there. So you get phi L as XBQ, right? XBP minus, so basically you are doing a rearrangement here. You basically get phi L, which is XBQ minus XBR by XBP minus XBR, which is basically, if I can take the other way, so I can take XBR minus XBQ, right? XBR minus XBQ is nothing but QR, and XBR minus XBP is nothing but PR. So basically I can do phi S also, which is again coming out to be PQ by PR. Right, you can do this algebraic manipulation and see, and basically you get phi S and phi L. So phi L is QR by PR and phi S is PQ by PR. So basically, if you look at that, you are looking at why is it called lever rule? Because see, you have Q, which is the alloy composition, which is your fulcrum, and you have P, which is your equilibrium solid composition, and this is equilibrium liquid composition, and this is the liquid arm and this is the solid arm. Now as you can see, phi L basically is liquid arm by the total length, right, of the lever. The total length is PR, and this is basically the solid arm by PR. And if you see that, if you look at that, if you move from Q to R, that is because the fulcrum is moving this way, right, you are going in here, then you have a small amount of liquid, right, as you go towards R, as you go towards the solid phase, then what you are telling is a small fraction of liquid is basically balancing a large amount of solid. Now if Q moves the other way, for example, then if you look at that, it is moving more towards the liquid. So if you move towards the liquid, then you have a small portion of solid is balanced by a very large portion of liquid, right? So when Q moves towards R, it is small amount of liquid balances a large amount of solid, and the other way it is the small amount of, so when Q moves towards P, say for example Q is moving towards P, if I tell Q moves towards P, then small amount of solid balances large amount of liquid. So small amount of solid balances a large, right? So we will basically the 10th week, all these lectures, I wanted to finish till lever rule because there is still the free energy composition diagram that is remaining, and there are some other phase diagrams where you have the solubility which is limited, right? Solubility in the solid is limited, solubility of A and B in the solid is limited, but solubility of A and B in liquid is infinite. So this is a special case where the solubilities of in liquid and solid are both infinite, but lever rule applies to any, right? A lever rule applies to any tie line, okay, for any composition, and that's why I derived the lever rule here. And remember, here we just one quick thing, that if you now look at the phase diagram here, so if you, as you can see, there is no horizontal line here. Are you seeing that there is no horizontal line here? Because as you can see, the composition is varying, right? So basically, if you look at, say for example, only here, only for the pure A and pure B, you will see such horizontal line. But other than that, you will see there is a continuous change, because as you can see, as you go from here to here, as you are coming down, right, you are here, say for example, your compositions are here, but as soon as you come here, then the composition has changed, right? So basically, if the composition is changed, no longer the cooling curve, because the conductivity has changed, everything has changed. It cannot be a single horizontal line, right? The single horizontal line cannot come here, right? You will have this sloping line and you have this continuous change in slope, right? This continuous change in slope is happening for any alloy which lies between A and B, right? If you are in pure A or pure B, again you will see a horizontal line, right? But when you are going as a mixture or a solution of A and B, then basically you can see the cooling curve that 2, which is in the 2-phase region, you see a continuous change in slope. And 3 is basically cooling of solid solution. Okay. So we stop here for the 10th week, and we'll continue with this more of phase diagrams and free energy composition diagrams, basically the thermodynamics of these phase diagrams.